right. Hello, hello. It is boiling outside. Is everybody swapping? I walked in here. I was like, oh my God, AC, dear Lord. So we're starting a new unit today all about sorting. So why don't you all take a few minutes, start out. Imagine I handed you a stack of papers. How would you sort it? Do you need extra space to spread things out? Would you find the next, the first one and bring it to the front? Go ahead, discuss amongst y'all, see what sorting algorithms you come up with, and then we're gonna spend all day today and Wednesday talking about some of the various sorting algorithms computer scientists have come up with. We'll check back in 4 minutes. All right, let's take a look at what y'all have come up with. There we go. Okay. This is a type I've never used before, so I was curious to see how this goes. Oh, interesting. Okay, we've still got answers coming through. Oh, some of us are looking ahead. Some of us are just calling out sorting algorithms by name. We fancy. Okay. BOGO sort. Effective. Efficient. These are interesting, actually. Okay. Let's see. Can I scroll through these? Let's do it. The slides aren't up for today yet. Is that true? Oh, shoot. Okay. TAs, if you feel compelled to ping the wonderful infrastructure team, cool. I mean, the slides are in the same place they always are. Oh, yeah, you could just ed post it. Oh, wait, let's... Okay, so let's... Sort. I see a lot of calls for merge sort. How on earth are you going to merge sort with physical papers? Are you just saying words that you saw in the slides? Does anyone want to actually raise their hand and tell me how on earth they would merge sort physical papers? Okay, then I'm going to assume all those merge sort answers are bogus unless somebody could actually tell me how you would apply merge sort to this scenario. BOGO, okay. You could BOGO sort it technically. Stack, sure. That's, yeah, stack, just stack. Ah, this is an interesting one. Make a stack for each letter and sort them from there. That is a type of sorting algorithm. I will introduce it. Yeah, see, I told you. We'll actually talk about that sort on Wednesday. Let's see what else is in here. Oh, I would do something like finding the middle letter and then sorting names by placing them. Oh my, that is also another sort we are going to learn at the end of lecture today. I am surprised. I didn't think that one was going to pop up. 26 piles, there we go. This one I would consider to be the same as this one. Let's see, separate them into A to C group. Aha, so a lot of these groupings, we would go maybe by letter. Yes, me and the TAs are having a laugh because this is actually what we call bucket sort, where you sort of separate the large collection in different buckets and then you sort within the smaller buckets and then mash them together because the buckets themselves are sorted. So you would have a bucket for all the A's and then sort all the A's and have a bucket for all the B's and then sort all the B's and then you could plop the B's after all the A's because you know they're in sorted order. Shout out, BOGO sort, very on brand. Okay. Stacks for each letter. Okay, BOGO sort certainly our winner there. Ooh, heap sort. Interesting. Okay. Bubble sort, yes. Ah, interesting. Sort by letter. This is another bucket sort here. I'm surprised. I truly thought that selection sort was going to come out on top. I thought you were all going to describe what you didn't know to be named selection sort. Let's see. Make piles. Ah, compare the paper at the top of the stack to the one under it and determine if it's less than, and then put them into the respective spot. Repeat until finished. Does anybody happen to know the name of that sort? That one's selection sort. That's the one that I sort of thought most people would do naturally, that you didn't even know that's called selection sort. But if you're holding the papers And you sort of look at the first two and you put them in relative sorted order to each other. And then you look at the third one and you put it in relative sorted order to the first two. Then you look at the fourth one. And so you sort of have this sorted stack versus unsorted. And you can kind of do it all in your hands that way, you know. Let's see what else is in here. Go over the paper by order and sort it along the way. I'm going to guess what that one is. I will say mine, the one that comes to my brain is I would probably like take the stack and then I would flip through from the start to the very end looking for the very first name. Like where is like A, the very first A name, and I'd grab it and I'd put it at the front and then I'd loop through again and I'd find the next one. That's what I kind of interpret this one. That one's called insertion sort. Okay, fun. If you are curious, I am not going to go over bubble or BOGO sort. If you're not familiar with those, go out onto the internet and have a good time. Okay, so here I tried to sort of imagine what some of y'all might say. I thought it was fun to get our brains starting to think in terms of sorting. Welcome to the sorting unit. Sorting kind of lives in a very special place in computer scientists' hearts. And for the next 2 days, we are going to be talking about a lot of different algorithms that technically all accomplish the same exact thing. And you might be like, Casey, why? Why are computer scientists so obsessed with coming up with more ways to do the exact same thing? And the honest answer is, I don't really know. I don't think we're realistically going to get any better than quicksort for primitives and timsort or whatever. But welcome to the obsession. You need to know it. And I think it's fun because it will teach you about algorithm design. So while we are going to talk about sorting algorithms for the funsies, really the big lesson of these next 2 days is when we're thinking about algorithms, how do we compare and contrast them? Okay. Okay, quick announcements. So exercise 5, that 2-week exercise is finally due today. Exercise 6 releases today. It's on algorithms. Exercise 6 will be on the 2 sorting lectures, and then we have the dynamic programming lecture on Friday. And then remember that the quote final exam, I'm using air quotes because it's only going to be an hour long and it will not be cumulative. So really it's just exam 2. That is on Friday, May 26th. It will be here in person. It will follow the exact same format of the last one, where we will do the in-person on paper one here. We will take it, we will grade it, and then you will get a resubmission. The resubmission is due the Wednesday of finals week then. So we will not have a class meeting or an exam scheduled during finals week. Does anyone have any course administrative questions at this time? Yes?
Does the regrade for the midterm open when the resubmission comes back?
Does the grade for the midterm open for the regrade? Oh, you'll have your regrades for the midterm.
When does the regrade for the midterm open?
Like, when do we get the grades back for the midterm?
Like, when can we submit regrade?
Oh, regrade requests. Like, is it open now? You're right. Resubmission grading is ongoing this Friday, till this Friday, yes. So this Friday, we're planning to have our TAs sort of wrap up the grading. We'll open up the regrade requests. You can regrade requests. Cool. Any other course administrative questions right now? Okay, let's dive in. So, where are we? Okay. This class is literally called Data Structures and Algorithms, and algorithms feel a little like neglected by week 8 of the quarter. Technically, all those graph algorithms we did kind of got us there, but we haven't really just talked about algorithms in their sort of separate sense. That's what this week is about. This is Algorithms Week. And so it makes sense because data structures are how we have to put all the data together. And then once all the data is together, then we run algorithms over it. We kind of saw that with the graph situations, right? So now we are going to talk about algorithms all of this week, technically all of next week as well, because we're going to do PNP next week. Very exciting. But a classic introduction to algorithms is sorting. This is a little bit one of those things where, like, Maybe I'm teaching you sorting because I was taught sorting, because everyone teaches sorting, and because everyone teaches sorting, we expect all of you to know sorting, and that's not a great way to teach something, but I have to be real with all of you. I gotta teach you how the game is actually played, and I can't let you go out there into the world or into interviews and not know the sorting stuff. So there is method to the madness, but maybe one of you somewhere in the future will free us of this particular obsession with sorting algorithms, but much more likely, many of you shall fall deep into the sorting algorithm obsession. Okay, types of sorts. So we are going to be talking mostly about comparison sorts. Comparison sorts are the type of algorithm that can be used to sort items of any kind. Meaning items that implement the comparable interface. So they could sort integers, they could sort strings, they could sort student objects if they implemented compare to. So we think of those as sort of general purpose algorithms. We are going to learn one niche sort, which is really the type of sorting algorithm where you can only apply it to a specific data type. For example, we're going to learn a sorting algorithm that can only be used on numbers, couldn't be used on strings kind of thing. But for the most part, we're going to be talking about comparison sorts. So there's a few different categories of sorts. So there are still some design trade-offs when we're talking about sorting algorithms. So truly, even in Java on paper uses two different sorts. But one of those sorts is actually a combination of two other sorts. So Java itself actually implements sort of three different sorting algorithms whenever you call arrays.sort. And that's because depending on what your goals are, you might have different needs. So some of the different goals, in place sort, if I call a sort in place, that means that I do not need extra storage. In our papers example, that's like you sorting all the papers still in your arms without having to like put them down on, surfaces or something like that. In code, that means you don't have to create a separate array to store things or something like that. Just whatever array I've originally given you, you just sort of swap things around. You don't use any extra memory. Okay, stability. This one's a little fuzzier than in place. So a sorting algorithm is stable if any equal items remain in the same relative order after the sort as before the sort started. So the reason this matters is because you might sort on one aspect of an object first and then sort on a different aspect of the object second. An incredibly relevant example. Canvas sorts all of you by last name, and then it sorts all of you by first name. A lot of you have the same last name. It happens, right? My stupid grade catalog that I actually use to put your GPAs in sorts all of you by last name, and then who knows what it does to first name, which is so stupid. And so I get the same order of last names, but I get a totally different order within the same last name, which causes me so much pain. You have no idea. And so this is an example of where stability matters. So what stability is I've gone through and I've sorted the items. Let's say they're a complex item. Like the student item, there was multiple pieces of data, a last name and a first name. Or let's say we have like numbers associated with animals. I don't know what I was thinking. I don't know why I picked that. So apparently we have the number 8 associated with fox and the number 8 associated with cow. You see in this original unsorted nature, the fox 8 comes before the cow 8. This would be a stable sort. I've sorted them so it goes 4, 8, 8, 9. I only sorted based on the numbers, but the 2 8s end up in the proper sorted place overall, but in the same relative position that they were in when we first started. If for some reason your sorting algorithm made the cow 8 come before the fox 8. That is not a stable sort. But, like I said, the classic example to me is sorting by last names, then sorting by first names. You could imagine if you have an unstable sort, I'm not guaranteed what necessarily the original order those names were placed in will be the same order relatively afterwards. Any questions on stability? Because this one's a little funky. Okay, great. Thanks, Pass Casey. Okay, cool. Okay, and then of course, those are sort of the new ones, but we're not losing our eye line to what we generally consider to be our most important analysis technique is the speed. We want sorting algorithms to run fast, especially because you will find in a lot of situations, whether it's a interview question or just implementing something, maintaining your data in a sorted order often makes it a lot more efficient, often makes it a lot easier to manage than just sort of totally unsorted data. So you will find that you do run sorting algorithms regularly. Maybe you run sorting algorithms on one original set. Maybe you run sort every time a new thing is added. So speed is often a very important factor when we are comparing sorting algorithms. Here is a list of some sorting algorithms. I do not know what all of these are, but I put the slide on here if you are, I don't know, down a YouTube wormhole or something. You could go watch all of these. Some of them, I will tell you, are absolutely jokes. Let's see, what are some good ones in here? I will say rainbow sort. My understanding of that one is that you take your data and you transform it into light wavelengths, and then you pass it through a prism, and then you retranslate the light wavelengths back into data. Yeah, I have no idea how they do it, honestly, but there's some cool YouTube videos about it. That you can see there's a ton of stuff in here. Like I said, I definitely do not know all of them, but we are going to talk about a good amount of them. Okay. So, like I said, my real goal with showing you all of these sorts is that you do need to recognize all these names in general, but I'm hoping to show you a little bit of the behind the scenes thinking of when people are going about and creating algorithms. Now, I know algorithm has become a unique cultural word. When I first started teaching computer science, nobody had heard that word before. Like, for real, I had to teach everybody what an algorithm was. And now, man, it's like algorithm is the new Florida man. Like, algorithm is always messing society up somewhere, somehow. Yeah? It is important. Hopefully, we are this deep enough into our lives with technology that we can appreciate how impactful, subtle decisions in an algorithm's design can be, and how it biases, how it chooses to surface information to you. If you are deeply interested in this type of stuff, there is a non-majors algorithms course. It's 417. There is a majors algorithm sequence, but definitely one big course. And you can take it, obviously, if you get into the major or if you want to petition into it. There's tons more stuff you can do in algorithms. And I also just take this moment to say, hey, y'all, we really, really need some fresh thinking, some different experiences and points of view in the algorithm design space. I say it to all of my classes, but if I was going to say one thing you could maybe get into that could truly transform the way the world works, is getting really deep into the field of algorithm design. Yeah. Okay. Anyway, that's my soapbox. Let's get into it. Okay, so here are some design patterns. So there's a few different contexts. We have sort of this invariance or iterative improvement type. We've kind of seen that. Those are like those greedy algorithms where we've got like a specific goal or a specific requirement, and our algorithm is just at every stage choosing the best choice to get us closer to that end goal, and Dijkstra's choosing the next closest node, right? That's a greedy algorithm. So that's sort of a step-by-step iterative improvement. Take a big problem, break it out into small steps. How do you eat an elephant? One bite at a time. That's that kind of idea. Then, separately, we have what we call the divide and conquer approach. I'm a little surprised that nobody in the warm-up was like, oh, I would like take my stack and split it up and hand a bunch of the stacks to my friends and have them sort those pieces, then we'd mash it all together. Guess what computers are really good at? Splitting up data and sending it off to all your little robots to ask them to do sub-portions of an algorithm and then mashing it all together. In fact, that's pretty much what computers are for, to take our hard sort of problems to solve, break them into a bunch of little pieces, stretch it across a lot of different computers, bring it back together. So that's called the divide and conquer technique. And then finally, there is the idea that we have learned some data structures that have sort of like requirements in their structure about the way and the order in which things are stored. What if we just use one of those? Then, like, the data structure is doing all of the ordering and sorting for us. So these are sort of the three main categories of sorting types that we are going to specifically go into. And you could definitely argue these are the three main categories of the most popular sorting algorithms. I'm not going to lie. I'm going to teach you the most popular sorting algorithms. The wild and wacky ones I'll let you look up on your own. Any questions so far? Let's meet a sort. Okay, yes. Okay, let's meet our first sort. Selection sort. Okay, so the way selection sort works is it is an in-place algorithm, and it falls into this sort of category of algorithms where it will start with your entire collection being marked as unsorted, and then it will loop and bring it closer towards sorted order on each loop. That's that step-by-step pattern. And every time you loop, the sorted portion grows and the unsorted portion shrinks until you have one completely sorted array. So the way it works is, let's say we've been selection sorting and we start at index 0 and we're working our way through. The next item we are ready to sort is 18. The way the sort works is it's like, oh, okay, it's time to sort, not so much 18, but it's time to sort position 4. I look through the rest of the unsorted array. I find the next largest thing, like the smallest thing in the unsorted section. So I find the thing that I realize should belong at index 4, and I swap. 10. 10 is in position 5. I look through 10 and all the unsorted things. Nothing is smaller than 10, so congratulations, 10, you're already in your correct spot. You can see how things are growing. 14. It's 14, so really it's 6 position spot. I look through the rest of the items. The next smallest item is 11, and I would swap it into that position. Wow, what an interesting way to learn about the sorting algorithm. But a far preferable way is, y'all, there is a YouTube video for absolutely everything. This is real. I'm not kidding you. They are my favorite sorting YouTube videos. This is an incredible troupe of real artists called the Algorithmics. And they do a series of Eastern European folk dances to demonstrate sorting. Wow. Come on, computer. Okay, all right. Yes, I need a new laptop. It's true. Okay, we couldn't ask it to do the whole thing. Let's start it at the beginning because they are so delightful. And their selection sort is truly an iconic. Okay, so they each have their numbers. They're in unsorted order. And so we're going to start at index 0. And there she goes. She starts looking. She's like, who is the smallest value in the entire collection here? Oh, did we find the next smallest value? I think the smallest value is 0. And so we're going to switch. And so she takes over Zero's original spot, and then Zero has his moment in the sun, and he compares himself because he was smaller than 3, so he compares himself to 1. She's not smaller. He compares himself to 8. 8 is not smaller, and then they are going to continue to loop through, and you will find that 0 was legit the next closest. So he is not going to swap with any of the rest of these wonderful dancers, and eventually will come to the conclusion that he does belong at index 0. Yes, indeed. Thank you, wonderful algorithmics. If you're like, wow, Casey, I didn't get enough, there's algorithmic dances for every one of these sorts. And they pick a different culture to represent each time. So there you go. Have a good time. Okay. So let's talk about selection sort. Here is some example pseudocode for you if you want to see how it runs. But let me ask this to the group now. What do we think the worst case runtime is? How many times am I going to touch every item in this collection before it ends up in a final sorted order? Congratulations. Yes. O of size. Ah, yes, like n being size. Okay, so O of size would be 1 linear pass. We are going to kind of start from the beginning, and we are going to move until it's finally sorted. But am I only going to touch each item only one time? Want to help us out?
I think the worst case would be n factorial, because you touch each one last time. Because if it's like anti-sorted.
If it's anti-sorted, and so if you do amortized analysis, what the idea was is like, let's imagine like it's like literally reverse sorted, and then it has to go through. That makes sense. But here's my question. How does any individual little dancer know that it is their turn to take their place? Do they have to talk to everybody? Do they have to compare themselves to everybody every single time? Okay, it gets less by 1, yes. But the original run, they have to talk to everybody. So the very first time, that very first one, it's going to come out of index 0, and it's going to compare itself to every single number. And then we're going to loop, and we're going to pull something out, and it's going to compare itself to every single number. And then we're going to pull something out, and it's going to compare itself to every single number. So I have like an outer loop, if you can see in our pseudocode there. That outer loop is going to run n times, n size. That's like the pass you were talking through, right? We're going to walk all the way through. But for each individual one, when they're like, ooh, is it my turn to go? There's an inner loop that also has to look over absolutely everybody. So this actually ends up being n squared time. You're right about the fact that it starts to get fewer and fewer, but the initial time is n times n run times, and so that will dominate. So this is an n squared sorting algorithm. And I will tell you, this is then officially on the extreme slow end of sorts. Of reasonable sorts, BOGO sort is nonsense. Okay, that's really literally n factorial time. So this is a worst case n squared sort. And our friend correctly identified our worst case scenario is if it is reverse sorted, or it's like totally unsorted, right? Does that runtime change in any way based on how sorted the array is? Like, it's always looking for the next smallest. Can it like bail out early? Any ideas? Yeah. I agree. It still has to check every single value. So selection sort, no matter what, has to look through everything in the unsorted list in every evolution to know that it has found the next appropriate item to place in that position. So we get this in practice runtime of n squared. Okay, what about stability? What do we think? Do we think this is a stable sort? I don't expect y'all to know how to do this yet, but do we have any intuition on this one? Yeah, sure.
My gut is no, because we loop through the entire thing. So say we have two equal values, it'll kind of pick the last one.
Yes, it is not stable. And here's the real secret, and you're right, because we're sort of looping through, but the real reason it becomes not stable is because we do those swaps. And so something that might have originally been at index 0, if it doesn't, like if that was its original position and we find something else to be at index 0, well then we're going to swap it with that item, and then later on we'll re-encounter it and swap it back in. Anytime you have this sort of swapping nature where you're sort of using other spaces within the array to store something to like come back to it later, that often will sort of mess up our stability. What about in place? Is this an in-place algorithm? Yes, yeah. We did not need any extra space, so we would call this an in-place algorithm. So, what is this one particularly good for? What's nice about this one is that it starts in sorted order, and every iteration, that sorted portion of the list is the final position. Every time you swap something into a position, that is its final position. So if you only needed the top K whatever, selection sort, just like get the top few out. Cool. Ready for another sorting algorithm? Yay. Okay, there's stability. You can read that. Let's talk about insertion sort. Insertion and selection sort are really easy to mix up, and frankly, I mix them up all the time too. Selection sort, the way that I keep that one is like you're looking through the rest of the list and you're selecting which one in particular belongs at that position. Insertion sort looks a lot similar to selection sort, as you can see here. We sort of start at index 0, we move and we sort of grow the sorted items while we shrink the unsorted items. But the difference here is that instead of finding the final resting place, everything's kind of staying in relative sorted order within the sorted portion. So let's say we're here at index 4. We ask ourselves, okay, 5, where does the 5 belong in the already sorted portion of the array? So instead of looping over the unsorted portion, I encounter the next item at the sort of boundary of the unsorted and sorted sections, and I ask myself, oh, where does this new unsorted item belong in my already relatively sorted items? And what's nice is that I'm going to find where it belongs, I'm going to pick it up, and I'm going to insert it into that location. So the 5 just got inserted in between 3 and 6. And then I'm like, 8, where does 8 belong? Oh, well, gosh darn, that's lucky. 8 is already in its proper position. Okay, 4, where does 4 belong? And then I would go over and I would loop over the sorted portion, and I would insert the 4 between the 3 and the 5. But remember, whenever I do insertions in an array, that triggers that, like, shifting shenanigan that happens. So, here's some pseudocode. What do we think the worst case runtime of this one is? I start at the first item, I ask where it belongs, I go to the second item, I loop over the sorted list, I insert it. Yeah. Yes, this is an n-squared one as well. It's again, we've got that sort of for loop on the outside, looping over the items we're trying to place, and then the for loop on the inside, looping over one of the subsections, this time over the sorted portion as opposed to the unsorted portion, but it amounts to the same thing sort of asymptotically. Okay, what about best case scenario? Yeah. Ooh, it is O of n. Do you want to explain for us why?
Yeah, because if they're in sorted order, it will just check once and then say, okay, I'm in the right place, and then just do that for each element.
Exactly. So if you have a list that is already sorted, what you're going to have is just a linear run through that's like, ooh, where do I sort this item? Oh, great, you're already where you belong. Where do I sort this item? Oh, great, it's already where it belongs. You just got to do a singular pass, which just gives us a linear runtime. However, that is very unlikely, so we consider this to be, in practice, an n-squared runtime. And generally, when you talk about insertion and selection sort, people just hear those and think, oh, those are the slow ones. Those are the n-squareds. But what about stability? What do we think about that? Do we think we could implement this with stability? Yeah.
I think stable because even like for the 8, when it checks where it should go, it would also check the other 8.
Yes. Yes, exactly. We have a lot more control in this case. We only ever move things when we are finally ready to know where they are going to belong relative to the other ones. In selection sort, remember we were sort of swapping things out of the way? And so it was like, throw this away for later. I don't know where it's going. But this time when we get to something, we're like, ooh, I'm going to specifically pick it up and insert it where I explicitly want it to be in relation to the other ones, so this can be a stable sort. What about in place? Is this an in place sort? Yeah, we didn't need to use any extra storage. And so then you can imagine that the thing that kind of sets this one apart is that it's really convenient if you already have a pretty sorted selection of things. That's nice. Questions? Yes, please. Ooh, okay, if you were using it to like stop early, so the outer loop then would only run k times, but the inner loop, to your point, would run over the entire thing looking for it, so it would be kn in that context. Yeah. Cool, great. Okay. This is just, I put a lot of I put a lot of details so you can read the slides later, but this is proving the stability thing. Okay. So that was principle 1, the step-by-step. Let's talk about this divide and conquer business. So the principle is computers can only solve really, really simple problems. And they're really good at breaking up complex problems into simple problems. And once we get to a really simple problem, we sort of mark it as solved, and then it's much easier for computers to sort of get to a good state and then recombine maintaining a good state. So what we're going to do is we're going to take a large collection of things that we're going to be like, whoa, that's too many things. I don't know how to sort that collection. We're going to split them into individual items. An item of 1 is sorted, and then we will recombine them. Great, cool. Insert, merge sort. Okay, so the way this works is that we give you a big sort of collection of items to sort, and then the computer's like, wow, is there more than one thing to sort? I don't know how to do that. Split it in half and let me pass that work along recursively. Divide and conquer very commonly is recursive because I like to think of recursive methods as it's sort of like a bunch of robots just like cloning each other over and over. Every time you make a recursive call, it's like, whoa, I don't know how to handle this problem. I'm looking for the base case, so just pass the buck along, kick that can down the road, pass that smaller array into 2 separate calls to the recursive call. I give one half of the array to one recursive call, I give the back half of the array to the other recursive call and let them figure out. And then those recursive calls are probably like, whoa, I don't know how to sort that many items. Split, and it branches out recursively until we get to a bunch of singular items. As soon as we get to a bunch of singular items, we're like, oh, well, an array of 1 is sorted. Great. Then, when we end the recursion, when we're sort of like rolling back up recursively, we take the 2 sorted arrays that we got from our recursive calls and we interweave them back together. We merge them back together. We just start at the front of each of those and we ask, who's smaller? That goes next, and we move. Who's smaller? That one goes next. Who's smaller? That one goes next. And we merge them back together. Great. You can read through a bunch of these things in more intense details. Okay, great. There's a lot of, here, this one's actually reasonable. We can talk about this. So here is how that merging works. We have returned back from our recursive calls. Right now, we have 2 arrays of size 4 that are each themselves already sorted. So the way the merge step works is we start looking at index 0 of both of the arrays, and we ask, who's smaller? Well, that goes in, and then I increase my pointer, and I look at the 2 pointers again, and I say, who's smaller? Well, that goes into my final position, and I increase my pointer, and I say, who's smaller? And I put that one, and I increase my pointer, and I say, who's smaller? Oh, there we got 2 from that side in a row. Okay, fine. Who's smaller? The 8 comes in. I move it up. I move it up. There you go. So any questions? I think the merge portion is the part that's the most complex here, because otherwise you're just breaking it down. The algorithmics also have a delightful dance, but I will not subject you to that. That one is particularly elongated. Okay, so here is some merge sort code, and here is a great, you can see. So you can see what it is. It's like if list of dot length is 1, just return the list. Otherwise, merge sort on 0 to mid, merge sort on mid plus 1 to the end, and then merge those two items back together. See how this is a merge sort method? These are the two recursive calls, and then I didn't have space on the slide, so that merge call there, that's the one doing the pointers and interweaving them as appropriate. Okay, once upon a time, way back in week 2 of this course, I introduced you to different recursive patterns, and I used merge sort as one of the recursive patterns of how the runtime grows, and I do not expect anybody to remember it, but we are going to represent this with a recurrence. Does anybody want to help me out with the recurrence? Can anyone remember how to write currences? What do we think the runtime for this is? Let's start with the base case. What is the runtime of just the base case of the recursive method here? Yeah, constant time. It's just like, return. Great. Okay. Now remember, in the branches of the recurrence, there is a call to the method again. There's probably a coefficient on that method call for how many recursive calls there are. And then what we put in between the parentheses of that method call is how the input changes. What would be the coefficient in our recursive branch for this one? Yeah. N over 2 is absolutely how the input changes. Yes, that's exactly. So if it's t of n over 2, that's how the input changes. And how many times do we make a recursive call? 2. Boom. That extra n hanging off the end there, that's the runtime of the merge. Because the merge is going to look at both of them, move from front to back. That's an n runtime. Does this algorithm change if the items are already sorted? What do we think? No, I still have to go all the way down to the base case. And in my merge, I still have to go from 0 all the way to the end. So, just so you know, if you do all of the delightful math, you end up with an n log n runtime. And the thing about merge sort, yep, thank you, past Casey. There we go. It's n log n no matter what. Totally sorted, totally unsorted, randomized sorted, no matter what, it's going to break it down and put it back together. Okay, what about stability? What do we think about that case here? Would this be a stable sort? Are we doing any weird swapping? No? Yeah, this ends up being a stable sort, which is really nice. Okay, what about in place? Is this an in place sort? No, because I'm making new arrays that total up to n at every single recursive level. So this is actually one of the more memory expensive sorts. But that n log n runtime is orders of magnitude faster than n squared. And in fact, I will show you a bunch of other sorts here, but you will find that for a comparison sort, everybody has been researching for many eons. The best you can do runtime-wise for the worst case runtime of a comparison sort is n log n. Now, we'll talk about the coefficients. It ends up a little faster this way and that and certain things when we get to quicksort. But overall, merge sort runs in the complexity class. It is the fastest we can do with a comparison sort. And it runs regardless of the sorted nature. It's very predictable. And because it is stable, this is kind of one of the sorting algorithms that Java uses when you call arrays.sort. and what's stored in your array is objects. Because it's objects where stability matters, you know? Any questions on this one? This is probably one of the most famous ones for a long time. If it was ever going to come up in an interview, this was the sorting algorithm they were talking about. This one in particular, like this is the Beyonce of sorts, all right? You could argue that she is not as good as people say, but they'd be wrong. Okay, great. Okay, we've got 2 minutes. I'm going to tease you with the next one. If I was going to make a sorting algorithm, I would name it quicksort. Genius move. So quicksort is also a divide and conquer, technically. We are going to split the arrays just like we did with merge sort, but the difference here is merge sort did not look at the values. It split based on the size of array. It was like the array too big, split in half. Quicksort is going to split based on what we call a pivot. And so we're going to pick a pivot and we're going to say everybody that is less than this pivot to one side, everybody that's greater than this pivot to the other side. And then we're going to recurse again and we're going to pick new pivots and we're going to split and split and split and split. And then the inexpensive action is the combine it all together. So where merge sort of is like, I don't want to think about it, just split. Then I'll think about it when I merge. Quicksort's the opposite. Quicksort is, okay, I'm going to intelligently split and then I can just mash it all together at the end. I will get into hopefully a little bit more of quicksort on Wednesday because this is the other sorting algorithm that Java uses. So come back on Wednesday and we will talk about how to pick a pivot. Thanks so much, everyone.